On this video, we're going to cover our exponential rules. So we're going to go over exponents. A lot of students find this section to be very frustrating because everything is based off a rule. Now, just like with the rational expressions and the factoring, I have a note sheet for you on all of your exponent rules. So here's all of your exponent rules. This can be found on Moodle, but there's all of the rules that we're going to cover. Please notice you don't have rules for addition or subtraction. So if you had x squared plus x, that's it. X squared plus x is x squared plus x. These rules are for when you have multiplication or division, or you have exponents on top of one another. All right. Let me get rid of this screen. You are going to see me switch between the book and the whiteboard, just because I want to make sure that you understand the directions. The directions of these are so important. Some of these I may actually work on as we go. All right. I'm going to have to get rid of this exponents. That's going to get on my nerves. We're going to do number 4 to start with. So number 4, they give me negative 3/4 in parentheses raised to the 0. Negative 3/4 in parentheses raised to the 0 is 1. That's what the rule tells us. Now, if that wasn't complicated enough, I'm going to give you a different problem. What if I give you this problem? It looks almost the same, right? The only difference is the negatives in the, outside of the parentheses, whereas in the first problem, it was in. The answer to this problem is negative 1. Anything raised to the 0 power is 1. And in this particular problem, the negative's on the outside, so it's not getting raised to the 0 power, just the 3/4. That's one of the reasons that this section gets so frustrating. The parentheses are a big, big deal. Depending on what's in or what's outside of parentheses will change your answer. Okay, let's look at number 8. Number 8, we have 4/3 raised to the negative 3. With this problem, there's a couple different ways you can do it, and that's another thing with the exponents. There's a bunch of different ways for all of us to work through these problems. I'm going to take the quickest route. When I see this problem, I'm going to try to fix the negative exponent first. So what a negative exponent does is it flips things. So what was on top goes to the denominator, what was in the denominator goes to the numerator. That's how you take care of a negative exponent. If I do that, I get this statement. 3/4, so it's all flipped. And the moment it all flips, this now becomes positive 3. So 3/4 cubed. Now, you can take the 3/4 fraction and cube it and say 3/4 times 3/4 times 3/4, or you do have an exponential rule that says, oh, just cube the top, cube the bottom. So 3 cubed is 27, 4 cubed is 64. So the answer to this one is 27 over 64. You will get really good at your cubes after this section. Okay, let's switch gears. I'm going to clear this. I want to look at, let's do number 16. So they do ask us to simplify each expression, assume that all variables represent positive real numbers. The reason they throw that line in there is it's easier on us. It keeps us from having to go in and say, oh, we have to make sure that X can't be this or Y can't be this. It just makes it easier on us. We're going to write our answers with only positive exponents. When you do your homework, they will not take negative exponents. Okay. What number did I want to do? Ooh, let's do 16. Do I have enough room to put it on the side here so we can look at this? I believe I do. So number 16, they give us 3z squared raised to the negative 1 over z to the 5th. Okay. Again, there are multiple ways to go about working this problem. It's up to you how you want to do it. I'm going to try to take the most straightforward way that I can. I'm going to give that negative 1 to both the 3 and the z squared. What that means is that this 3 is now going to be raised to the negative 1, and this z is now going to be raised to the negative 2. You have a rule that says if you've got ab to the n, or whatever variation of variables I have on your note sheet. It's a to the n, b to the n. You also have a rule that says if you've got a to the m raised to the n, that's equivalent to a to the m times n. I'm having to apply both of these rules to this problem. This first rule is how I come up with this. And the second rule here is how I got this -2. Because the z had a 2, I have to multiply those exponents. Okay, so you've got 3 to the -1, z to the -2 over z to the 5th. Let's fix our negative exponents. Now notice your rule says if you've got a to the, how do I have it wrote? I think a to the -n is how I've got it wrote. That's equivalent to 1 over a to the n. What that means is if you've got a negative exponent, to make it positive, it does need to flip either, if it's on the numerator, it goes to the denominator. If it's on the denominator, it goes to the numerator. So it flips whatever direction you need it to go to make it positive. I'm going to take this and flip it down. I'm going to take this and also flip it down. The one thing that I am not going to touch, however, is the z to the 5th. It is a positive exponent. It's going to stay exactly where it's at. So when I flip the 3 to the -1 and z to -2 on the bottom, I'm left with a 1 on top. Okay. One more thing I can do here. You see the z squared and the z to the 5th? That's the same base, correct? When you're working with exponents, that's what you're looking for. You're looking for the same base to clean things up. So you have a rule that says if you've got a to the m times a to the n, you got the same base and you're multiplying, that's equivalent to a to the m plus n. That means I'm going to add these exponents. You actually already know that. This is the same thing that we were doing when we were doing our, I think we were working with polynomials. I think that was the name of the video. When we would multiply, we'd add the exponents, and when we divide, we subtracted. Same idea. So that's where those rules come from. If I use that rule, I'm going to have 1 over 3. I don't need the 1 on the 3. And z to the 2 plus 5 is 7. And that is my final answer. Where it says right answers with only, or no, excuse me, assume that all variables represent positive real numbers, that's what allows me not to have to try to fix this z and make sure, oh, you know, it doesn't go to 0 and all that. Okay. Let's switch gears. Here. So many rules and so little time. I want to look at, let's do number 32. No, I'm going to back up. Let's do number 24. There we go. So we're going to simplify each expression, writing the answer as a single term without negative exponents. Ooh, now something's weird about number 24. Number 24 is an addition problem. If you remember at the beginning of this video, I said our exponential rules do not apply to addition. So I'm going to clean what I can up using the exponential rules, but it's not going to be the exponential rules that ultimately solves this problem for me or fixes it in the form that I need it. Number 24. M over 3 to the -1 plus n over 2 to the -2. Okay, let's get rid of the exponents. And to get rid of those exponents, let's start with the negative. To fix the negative, I'm going to flip my fractions. And I'm going to flip the whole fraction just because everything's in parentheses. So that negative belongs to everything in the parentheses. So this first fraction is going to become 3 over m to the 1. And the second fraction is going to become 2 over n to the 2. Notice the negatives are now gone because the fraction flipped. That was the rule. 3 over m to the 1 is just 3 over m. Here I've got this squared, so what I'm going to do with that squared is I'm going to give it to everything. So I'm going to have 2 squared over n squared. And I can clean that up just a little bit more. 2 squared is 4 over n squared. At this point, I have used all of my exponential rules that I can use. I can't do anything else with this problem using the exponential rules. So I'm going to have to go somewhere else. I'm going to have to do something. They do ask me to write it as a single term. I can't leave it like this then. I gotta get it together somehow. So I'm going to go back to your rational expressions rules. Because I've got two fractions and I'm adding, I need to find a common denominator. My common denominator is going to be all the different versions of what I see on the bottom of these denominators. So I see an m and an n squared. That means that my LCD is going to be m n squared. So what's this first fraction missing on the bottom? Well, let's do it a different color. We are definitely missing an n squared. So if I give the bottom an n squared, I have to give the top an n squared. That second fraction, I am missing the m. So I'm going to multiply the bottom and the top by an m. If I do that, I'm left with 3n squared over mn squared plus 4m over mn squared. We have the common denominator. Both things have the same thing on the bottom, so I can put them over one denominator, the same one. So I'm left with 3n squared plus 4m. That is my final answer. That is as combined as it's going to go, but we do have a single term. Whew. Okay. Variables are fun, but let's make sure that we understand what's going on with numbers as we go through this. So I'm going to look at number 32. Scroll up to where we can see number 32. Directions say write each number without exponents. So on number 32, we're given 64 over 27 raised to the 1/3. Okay, you have a rule that says if you have a to the 1 over n, that's equivalent to the nth root of a. Or I could write it like this: if I have ab to the 1 over n, that would be equivalent to the nth root of a over b. Or the nth root of a over the nth root of b. You can split it up. It means the same thing. All right. So if I rewrite this, this is equivalent to saying the cube root of 64 over 27, which means that I can take the cube root of 64 over the cube root of 27. In other words, what would I have to cube to get 64? Well, that would be 4. And what do I have to cube to get 27? That would be a 3. My final answer here is 4/3. It's not hard, but it can be confusing with all of these rules that you have to keep track of. Let's look at number 40. Simplify each expression, write all answers with only positive exponents, assume all variables represent positive real numbers. Cool, makes it easy. Easier on me anyways. Okay, 40, we've got 3 to the negative 5 halves times 3 to the 3 halves over 3 to the 7 halves times 3 to the negative 9 halves. Whew. One of the things that's so nice about number 40, though, is that you do have the same base. You have a 3, a 3, a 3, and a 3. If you had like a 3, a 4, a 5, and a 6, you couldn't do anything with it because it's different bases, and your exponential rules don't work for different bases. But we're in good shape. On top, you've got a base of 3 to the negative 5 halves times base of 3 to the 3 halves. When I'm multiplying, I can add the exponents. So if I add negative 5 halves and 3 halves, I'm going to get negative 2 halves. So I've got 3 to the negative 2 halves on top. Let's look at the bottom here. Same thing, I've got the same base. I'm multiplying, I can add the exponents. So I'm going to have 3 to the negative 2 halves. Guys, I can already tell you that this answer is going to be 1 just because I've got the same thing on top and bottom. Let's say you don't catch it, though. That's fine. There's nothing wrong with that. If we keep working this out, you're going to have 3 to the negative 1 over 3 to the negative 1, because negative 2 divided by 2 is negative 1. You can flip it. Either way, you're going to get 3 over 3, which is still 1. So the answer to this one's 1. Don't you love it when you have this problem that just looks so complicated and you end up with an answer of 1? All right. Let's finish on a high note here. Let's do, oh my goodness, I want to do 50. Look at that. That is just beautiful. So number 50, same set of directions. We got to clean it up. They give me m to the 7/3 times n to the negative 2/5 times p to the 3/8 over m to the negative 2/3 times n to the 3/5 times p to the negative 5/8. Ooh. All right. Looking at this problem, the first thing that I noticed is I don't have the same base on the top. I've got an M, an N, and a P, which means I can't do any work together on top. Same thing on the bottom. I've got an M, an N, and a P. I can't do any work together on the bottom. But I do have an M and an M on top and bottom. I have an N and an N on top and bottom, and a P on top and bottom. So that's how I'm going to attack this problem. The reason that we are able to do it this way is because I don't see any addition or subtraction in this problem. This is a monomial. So I'm allowed to work with the M's individually and the N's individually and the P's individually. If I saw any type of addition or subtraction, I could not do this problem the way I'm going to show you. All right, so let's look at the M's first. You've got M to the 7/3, you've got M to the negative 2/3. This is a division problem. Your division rule says that if you've got a to the m over a to the n, that's equivalent to a to the m minus n. So to divide, we subtract the exponents. I'm actually going to write this out so we can look at it. So if I look at the m's, I'm going to take my 7/3 minus my negative 2/3. So notice your rule has a standard minus sign, which I put in here, and you also have to account for the negative that you have in the problem. So 7/3 minus negative 2/3 equivalent to plus a positive. So that's 9/3, which is 3. So I'm going to have m cubed. Okay, let's look at the n. I've got negative 2/5 minus 3/5. Negative 2/5 minus 3/5 is going to give me negative 5/5, which is equivalent to negative 1. So I've got n to the negative 1. And then p, I've got 3/8 minus 3/8 minus negative 5/8. Of course, minus the negative is the same thing as plus a positive. So we've got 8/8, which is 1. So I've got p to the 1. I wish I was done. But remember, the directions said you cannot write this with negative exponents. So I do need to fix this n to the negative 1. The m and the p are fine. It's just the n to the negative 1 that I don't like. So my m and my p are going to stay right where they're at. And I don't have to put p to the 1, just p. This n to the negative 1, though, is going to flip down, and it's going to be n to the positive 1. Again, I don't need to put the negative, or excuse me, I don't need to put the 1, because if you've got an n, you've got an exponent of 1. Scary looking problem, but as long as we know our rules, it's not that bad. Yes, so that finishes up all of our information on exponents. Again, if you have any questions, let me know.